All right, so let's talk about energy. So last class period, you were supposed to do the energy introductory lab, which was the skate park on the PhET simulation website. So let's expand on that for a moment, but let's talk about what you should have learned in the lab. Okay, the lab asked you to look at several things. Okay, so first they wanted you to have a track with at least one hill and one loop. So something really basic could have looked like that. Okay, you draw it out, and then you were supposed to start your skater on the track. So it says here to place the skater at the top of the track. So then it says, did it complete it or not? So your situation is going to be a little bit different depending on what your coaster looked like. So they may have made it, they may not have made it. Okay. The biggest things you should have found were that the ones that had the most potential energy, and we're going to get a little more specific with what type of potential energy this was, but you should have saw that the most potential energy was the one that started at the highest height. Okay. That's where the highest potential energy was. Well, then the least potential energy was at the lowest height, or when you were at what was called the reference position. Okay, that's our 0. So we're going to be talking a lot about a reference point or a reference position, because that's really important. Things can have gravitational potential energy, which we'll talk a little bit more about. Relative to the floor, if it's sitting on a desk, but relative to the desk itself, it wouldn't have any potential energy. So we'll talk about that when we get there. Okay, the most kinetic energy should have been the highest velocity. So whenever it was moving the fastest. And the least kinetic energy was the lowest velocity. So potential energy you should have found was related to the height that the object started from or was located at. And the kinetic energy was the velocity. Okay. All right. In the table below, describe what happens to the potential and kinetic energy of the skater when he's on different parts of the track. Okay. So here's the hill and then goes like that. Okay. So high on the track is up here. So the higher you up are on the track, the higher your potential energy is. Okay. The middle of the track is where you're starting to get a decrease in potential energy. Okay. And at the bottom of the track, you have 0. Okay. So I guess you could say it decreases again. All right. So middle of the track and bottom. So you should have seen that potential energy decreased all the way down the track like that. And I should use a different color. Then as it starts going back up, okay, so it's on the way back up the track, then it's increasing, okay? So you're going to have to look at that. So as he's going back up from here to here, then we start to get an increase of that potential energy again. And then from here to here, we get an increase again. But when you're going this way, you get the decrease, okay? The kinetic energy, it's exactly the opposite. So the higher you're getting on the track, the smaller your kinetic energy is becoming because it's slowing down as it goes back up the hill, okay? About in the middle, it depends on where you are. So if he's going down like that and we're at this midpoint, then it's increasing, okay? Once you get to the bottom, it still increases. That's where it's at the maximum, okay? And then, so increases when we go this way, and it decreases when we go back the other way, okay? So exactly the opposite of what's going on with the potential energy. So we'll talk about that when we talk about energy transfer, and energy conservation. Okay, so it says, what claim can you make between the relationship between kinetic energy and potential energy? Well, I just talked about that, okay? So as the potential energy increased or increases, then the kinetic energy decreases. As the potential energy decreased, you should have saw an increase. Oh my gosh, that was a terrible E I just drew there. Your kinetic energy increases. All right, what is your evidence? Well, your evidence was as it got higher on the track, you saw more bars on that potential energy in your bar chart, and you saw less in the kinetic. And then as it got down to the bottom part of the track and it was going faster, you should have seen an increase in the bars for the kinetic. Okay. So where's the speed of the skater the greatest? You should have saw that it was the greatest at the very bottom. This is what we would call our reference point or our height of 0. Okay. So that reference point is going to be really important, and we'll talk about that some more. Okay, so when he's on different parts of the track. So, now it is... Oh, what did I do? Skip ahead one? Oh, no, it was the same page. Hello, I am losing my mind. Okay, so what they're asking for here is basically the same thing. We already talked about that. And then you were supposed to measure the speed of the skater, and then they wanted you to look at it. We've kind of already talked about that there. We're going to go more into detail when we talk about the types of energy in a moment. So it says, in the space below, find ways you can change the total energy in the simulation. So the ways you could have seen was changing mass. I don't know if you can change the skater's mass on there or not, but you should have saw a change in total energy if you change the mass. You could also see a change if you change the height or if you change the speed in some way. Okay. Now, you can't really control the speed because the speed is going to be related to the height. So what you were really changing was the height of the track. But if there was a way to make this skateboarder speed up, like you could add a motor or something to the skateboard, then you could increase the total energy that way. Okay, so friction changed a little bit. We will talk a little bit about that in the slideshow. You should have made some observations there. Okay, so you should have saw that with lots of friction, you had a decrease in the skater's motion. If you had no friction, you had an increase. Okay, so the friction caused the skater to slow down. You could have also saw that he didn't go up to as high of a height as he did previously. And those are all observations you can make. Okay. Then they had you do some making your own track, and then they had you labeling some things. We'll go back over that later, but I want to get to the types of energy. So let's talk about that. Okay, I will put a copy of this slideshow on in the module along with this video. There will be a link because I think it's really important that you can see these are not pictures here. They look like pictures to you guys because they're static, but they are not pictures. They are it's a slideshow with GIFs in it. So there's actually motion going on in this picture in the slideshow. So some of those are going to be important, and I'll talk about which ones you might want to go and look at to get a better visual of what's going on with the energy. Okay, so first of all, we're going to be talking about the total energy of a system. So we're going to have some different variables here, and we're going to have units. So let's go ahead and talk about the basics right now. So the units for energy. The units of energy are joules. They are named after a person. You can look it up, but we're going to use joules, and it is a capital J, okay? So anytime you're calculating energy, you're going to talk about that energy being measured in joules. Just like if you were talking about mass, you would talk about the mass being measured in kilograms. We are going to be talking about systems. You're going to hear me say that a lot. You guys aren't really going to have to worry about the system idea, but I teach AP physics also, and systems are a big idea in AP physics. So I can't talk about energy without talking about a system. But basically, it's the same thing we talked about in forces when we talked about the system. So everything that was interacting, and we will be talking about things that are not in the system, and we're going to talk about how those things interact together and how we can move energy into a system and move energy out of a system. Okay, so we are going to be talking about total mechanical energy. So most of the energy we're going to talk about is mechanical energy. Don't get too caught up on that, especially the mechanical part. There are some books that use and websites that use what's called thermal energy, and we'll talk about that as TE. So we try to avoid using TE for total energy, because if you go look up TE and they're talking about thermal energy, they are not the same thing. So we're going to use total mechanical energy. That is just the total energy in the system. All right, so let's talk about this idea of energy. Okay, so there's different types of energy, and there's different ways to add energy to a system, and there's different ways of removing energy from a system. So let's talk about this idea of putting energy in or taking energy out first. Okay, so your skateboarder, when he was on the ground, before you did anything with him, he had no energy. He was just at rest, standing there. You had to build a track, and you had to place him on the track. And I have never said I was good at drawing, so bear with me, okay? There's your skateboarder. When he was down here, he had total energy of 0. Or she, girl skateboard too. Okay, so total energy is equal to 0 down here. When you picked him up and placed him up here on the hill, or her, you put energy into that skateboarder track system, okay? So the way you transferred energy in, we call that in physics work or working. So working or work, you're going to hear me say it both ways, is the transfer of energy into, so the total mechanical energy goes up, or out of. That's where your total mechanical energy would go down, okay? The system. We use W for work. We are not going to go into equations today. We'll do that next time. But you're going to need to know these things when we talk about them next week. Well, you're going to need to know them for the practice today, but you're going to need to know them next week too with the equations. But we're going to not giving you the equations today. So leave some space there if you want to add the equation in later. Otherwise, when we go back over this, you can do totally new notes. It's up to you, however you want to organize it, okay? But working is transferring energy into or out of a system. It's not the same type of work we talk about, like we go do a job somewhere, but the idea is kind of the same. The more work you do, or the more hours you spend at your job, the more money you can transfer into your bank account, okay? It's the same kind of idea. The more forces do work on a system, the more energy the system has, okay? Well, let's talk about how we can get work done on a system, or how the energy can increase in a system. So we talked about all these forces except for this one. Actually, I'm not going to erase it because we are going to talk about something that has to do with the spring. So a spring force, like I said, we didn't talk a lot about. So we did the Fab 4 for our forces. But there's really also a force you can get from a spring, okay? So any of these forces can do work on a system to transfer energy into that system or transfer energy out of the system, okay? You can only have that increase or decrease in energy if you have one of these forces acting on an object. So each of these forces is going to have something to do with a type of energy. So let's go ahead and talk about those types of energy. All right. Oh, did this jump ahead? No, that's the first one. Okay. Elastic potential energy. Okay. So elastic potential energy, the variable is US. U means potential energy. And the S, I say, is easiest to remember it as standing for spring. Okay. So potential energy from a spring. All right. We know an object has elastic potential energy if a material or a spring is stretched or compressed, okay? But it has to be stretched or compressed right now. I cannot write well tonight. Compressed right now, okay? And we're going to do steps again. I'm big on the problem solving steps. Right now, we're just kind of identifying our types, okay? So in order to have elastic potential energy, you have to have something that can be stretched or compressed, that when you let go, it's going to spring back, or when you pull a trigger, okay? Once it's not stretched or compressed anymore, it's no longer going to have that elastic potential energy. Okay, so we do not do that in honors, so we can skip that one. All right, so gravitational potential energy. So what's the force in our gravitational field? We've talked about that before. So Fg is your gravitational force, or your weight, and it equals mg. And then how do we know an object has gravitational potential energy? This is the one you did in the skate park. So we look for a height, okay? So is it at a height above a reference point? When we talk about the equations, we'll revisit this a little bit more, and we'll tie it together with this. We're not doing any equations today. But the more height something has, you saw it in the lab, the more gravitational potential energy it has. All right, kinetic energy. How do we know an object has kinetic energy? It's moving. Okay, so if it's moving, it has gravitational, or it has kinetic energy. All right, and how can we calculate it? We're going to talk about that next time. Okay, so we're not going to talk about that one just yet. We're going to talk about it next time when we start tying these ideas together. The big idea you need to know right now is that it has kinetic energy when it's moving, and the faster it's moving, the more kinetic energy it has. Oh, I forgot to mention this one. It's going to be UG. This is how we represent gravitational potential energy. U for potential energy, G for gravitational. All right, kinetic energy, we're going to use KE. K for kinetic, E for energy. All right, so total mechanical energy, we've talked about this. We can find it anytime by just adding up all the different types of energy, okay? So these are the 3 types of energy we could have in our system, and we add all those together, whichever ones we have, and that'll equal our total energy, okay? So we have this law of conservation of energy, okay? So we're going to talk about this law of conservation of energy a lot. What it tells us is that the initial or starting total mechanical energy has to equal the total or the ending total mechanical energy, okay? In a closed system, you don't have to worry about that definition, but that just means there's no energy transfer into or out of the system. All right, let's talk about our steps real quick, and then we'll talk about the practice. All right, so for the steps for solving energy problems, all right, step 1, what is the energy? So we have to know what energy is there. So we need to look at 3 things, okay? The first one is it above or below? There may be situations when you're below a reference point. Okay. So is it at a height is basically what you're looking for. If yes, then you have gravitational potential energy. And we're going to give you an equation for that, but we're going to do that next time. If it's no, then there is no gravitational potential energy, okay? So, if there's no gravitational potential energy, the height is 0. If there is gravitational potential energy, the height is not 0. All right. Is the object moving? If the object is moving, then we have kinetic energy. And again, you're going to get an equation for that next time. If it's not moving, then the kinetic energy equals 0. Okay, so that means it has a velocity of 0. Over here, it means it has a velocity or a speed that is not 0. Okay. All right, next question. All right, the third question is there a stretchy material or a spring being stretched or compressed right at this moment that we're looking at right now? If there is, then we have elastic potential energy. We're not going to make you guys know the equation for that one, so we're just strictly looking at whether it's there or not. If something is not being stretched or compressed right now, then the elastic potential energy is equal to 0. Okay, so that is step 1. What is the energy? What type of energy is there? So the next step we're going to look at is step 2. All right, and step 2 is going to have to do with writing the equation. Before we can write the conservation of energy equation, we need to look at if there is friction. So is there friction? Okay. And remember, these steps come after you define the system. So I really should have had a step 0 that was defining your system. But once you see what the practice problems look like, that'll be easy to know that you need to define your system. All right. So is there friction? If there is friction, then that means the total mechanical energy at the beginning has to equal the total mechanical energy at the end plus whatever work was done by friction. We're going to label the frictional energy as, E for energy and dissipated, okay? So the total mechanical energy, you can also just abbreviate that with E if you want to. It makes it a little easier to think of total energy that way as well. If there is no friction, then the law of conservation of energy means the initial energy has to equal the final energy, okay? Or the total mechanical energy initial equals the total mechanical energy final, okay? They're the same thing. Total energy, total mechanical energy. It's just your total energy that's in your system. All right. Last but not least has to do with, not last but not least, step 3. Is energy being transferred into or out of the system? Okay, so that is there something that is not inside our defined system that is doing something to add energy into the system? Okay, so if energy is being, work equal to 0, oops, that's not what I meant to write. Okay, so if energy is being transferred in or out, then work cannot equal 0, and we are going to give you an equation for that next time. If it's not having energy transferred in or out, then the work equals 0. Okay, so once we know that, then we can go to the very last step, which is do the math. Okay, so if you have numbers, then you're going to do the math last. Okay, so let's summarize a little bit what we talked about then. We talked about the units for energy. And we said that those were a joule, We talked about work or working, and the variable we're going to use for that is a W. We talked about kinetic energy, and the variable for kinetic energy we're going to use KE. We talked about gravitational potential energy, and we'll give you equations for these next time. Gravitational potential energy, we're going to abbreviate, not US, with UG. And let me write that more. I'm trying to be better about my subscripts. That's going to be a subscript. Stretching or compressing of a material. I don't know why I just wrote the definition. I meant to just write the name. If we're stretching or compressing a material right now, we have elastic potential energy. Or you'll hear me call it spring potential energy, and that's only because our variable is U. I don't know why I wrote my U like that. It's U with the subscript S, so it's easy to think of S for spring, and if it's springing material. Let's see. We talked about total mechanical energy. And I will let you use for variables for that either just E or TME. Let me write that so it doesn't look confusing. So either just E for total energy or TME for total mechanical energy. And then we also talked about the energy that is going to be attributed to friction. Frictional energy is actually heat energy. But we're also going to lump into this light and sound. Okay. And we're going to call this E-dis. And dissipated means not usable energy. Okay, so how I want you to think about this is we talked about doing some work, and the more work you do, the more energy or money you can put into your bank account. Well, eventually you're going to use that money you've been putting into your bank account to go buy something at the store. And you're going to give some of your money or energy to the store clerk, and that energy or money is going to go in their cash register. We do not talk about energy being lost because we know where the energy went. Just like when you gave the store your money, you know that your money went to the store. You no longer have access to that money. So you can't use that money without stealing it or doing something illegal because it's not usable to you anymore. And heat, light, sound. Now we can get energy from light, so let me not use that one as an example. But energy of friction, which is heat, and sound, we can't get usable energy out of that. So that's that energy we talk about not being usable by the system anymore. Okay. But we have to account for it because we know where that money went or that energy went, and we have to account for it in our equations. So you have practice problems over this you need to complete. You will have a quiz next class period over the practice problems. If you have questions, please let me know. I will do a couple of example problems out of the practice in a separate video. So enjoy the rest of your day.